Okay, so we are at the change of phase. I think all of you know. So whenever we change in phase, you should know that it can be from solid to liquid and to gas. So we are in this topic, we're going to discuss only three of the phase: is solid, liquid, and gas. So here, solid to liquid is melting. Liquid to gas is vaporization or vaporization. So this is so gas to liquid is condensation, and liquid to solid is either solidification or freezing. You can use freezing as well. Okay, so each of these, whenever we are solid, let's say if I were to have an ice at negative 15 degrees Celsius, so if I were to heat up this ice, the ice firstly not going to melt, okay, because we know it only melt at 0 degrees Celsius. So what happened is that the temperature going to be increased. So this is increase of heat, and then this is increase of temperature. So when I increase the temperature, heat, I provide the heat, what happened to the ice? The ice will increase in temperature, and then once it reach 0 degrees Celsius, so this is before that is 15 degrees Celsius, and then when it reaches 0 degrees Celsius, it will maintain the temperature. So maintaining the temperature, the reason it's maintaining temperature, it is because the energy is being absorbed. If you look at here, it still go to the right, which is still absorb more energy, because that energy is being used to break the bond. For this case, it's solid to liquid, to break the bond of solid. So here going to be a mix of solid and liquid, but the temperature remain the same until all of the solid is been have melted away, then only then the liquid going to start increasing in temperature. Then of course the temperature will increase until 100 degrees Celsius, and then what happened here is there's a boiling point where the water start boiling, and then when it boils, it's turned to vapor, and then you will see the maintaining temperature as well. Although that you provide a continuous heat to the water just now, to the liquid of water, and then what happened, all the water continuously change into steam until all of the liquid water turn into steam. Then if this steam been contained, and then you further increase further provided heat to this water that has been vaporized just now, so it's steam of water just now, then the steam will again continue to increase in temperature. So for change in phases, we call it the heat required to change in phases is what we call latent heat. So latent is mean that it's hidden, because the reason is hidden because the heat being absorbed, but it's not increased in anything. The temperature does not increase in any way, okay, until all the material have changed phase completely. Okay, so this is the illustration of a solid. Solid is very packed together, the particles, whereas in liquid it's going to slightly to be separated, where the particle can be sliding among each other. You can follow the form of its container. So the gas is technically quite similar to liquid, where you can fill in the follow to the shape of container, but the gas is much more free. Okay, it's much more free, so you can fill up the container even more easily, and then the separation between the particle is much more further. Okay, so the equation for the heat required to break this bond, we call it for phase transition, heat for melting point, for melting is Q equal to ml. So m is still mass, Lf is a constant. It's a constant specifically for each metal going to be different. So Lf is a latent heat of fusion. So fusion is for melting from liquid solid to liquid, or for freezing. It's the same thing. Okay, it's the same thing. It's only that for freezing, the Q going to be negative, because the material going to be dissipating the heat. Dissipating the heat going to be negative. So as we go to liquid to vapor, So the same process, if you look at here, we're going to the calculation also going to be the mass and also the constant for latent heat. But here the latent heat is going to be not the same, although it's the same materials, not going to be the same. Whereas the latent heat is latent heat of vaporization. Latent heat for vaporization. Okay. So if it goes to condensation, means that from the gas to liquid, the latent heat also going to be the same, only that the energy should be in negative. Okay, you should introduce a negative sign upon to that process of the other way around, vapor condensation, from gas to liquid or from liquid to solid for fusion process. Yes, fusion process. Okay. So this is the definition. You can go to here. Okay, I already explained all this thing. Okay, so this also I'm going to explain. So technically, whenever what kind of equation you're going to deal with is that here, when it receives heat, it's going to be that heat going to go to the mc del T. As for this one, it's going to be q to ml fusion F. And then here go back to q to mc del T, and here you're going to go to q to ml. So this one is vaporization, and then here you're going to go back to mc del T. Okay, so I think for vaporization, for fusion and vaporization, I think we already cleared that. So here we just need to know the mass here going to be the same. Let's say if I were to melt the ice and then ice become water, so the mass is going to be the same all the way through. Okay, but here for specific heat, the ice will not be the same as water, will not be the same as the steam. So each of these phase will have, although it's the same material, but it is a different phase, so the specific heat capacity is also going to be different. So you need to make sure that you use to the right condition. Okay, so this is what I explained just now. Okay, I think that's all. That's all. We can just so this is the specific latent heat of fusion and then latent heat of evaporation. Usually all this constant will be given to you, but you can see that what we can discuss regarding on this value, you will see that the latent heat of fusion to melt. So we have copper solid, then let's say we have what you call that, nitrogen. So although that copper and nitrogen, if you look at here, of course we can't see the nitrogen solid in our daily in our normal condition in room temperature, but we can see copper easily in the room temperature. But if you look at here, there's not much of difference in heat, latent heat of fusion. So remember that this is the amount of energy to break the bond. It is not depend on the temperature. The temperature, of course, it depend in order for you to heat up. So in order for it to melt, it required to reach to the melting point. Remember that melting point is not about energy, it's reaching to the melting point. So that the reason the melting point of nitrogen is very low, so that's why we hardly, technically it's impossible for us to see any nitrogen melting in our unless you bring it, of course you can see, but in a normal condition, so you can't see solid nitrogen anywhere in the room temperature, because it's already, everything is already turned to gas because of the melting point. It's very low for nitrogen compared to copper. It's very high. But although that the what you're seeing here is not comparable into when it's going to melt, but how much energy is required to melt. So but still you will see that copper require more energy to melt from solid to liquid compared to nitrogen. If you compare to the ammonia, it's even much more energy required, although the ammonia is also can be in gas, in our room temperature. Okay, so that's all. Okay, let's try one of the example here. Okay, if you look at here, let's try number 2 here. How much energy is required to change a 40 gram of ice cube at 10 degrees negative degrees Celsius to a steam of 110? Okay. So when this happen, if you need to illustrate where does it start from. So it start from -10. So this is again temperature in Celsius, and then this is amount of energy. So it start from -10. So whenever you heat up, okay, it's going to first increase in temperature. So when how much it's going to increase temperature? Up to 0 degrees Celsius, and then it's going to constant until everything going to melt away, and then again increase in temperature to what? To steam. So when will it reach to steam? At 100 degree Celsius. And then after that, what happened? Again, it's going to be constant. Again, it go to the vaporization process, and then after it done, again it will continue in temperature. So what will be the last temperature here we're looking for? It is going to be at 110 degrees Celsius. Okay, so how to determine this? Okay, remember that this is the question is about how much energy. So how much energy? So we already done this before. So how much energy to increase a certain let's say if I were to say how much energy to increase question 1 tu lah. Okay, if you look at the question 1, how much heat required to boil away not that one. How much energy required to increase 200 gram of water at 27 degrees Celsius to 100 degrees Celsius. So how to solve this? It's just Q equal to M. M is 0.2, which is the 200 gram. The specific capacity for water is 4200. I just took from here. And the temperature difference. So the last temperature is 100. The initial temperature is 27. So solve this, you're going to get the answer for heat required for water to increase its temperature to 70 to 100. So the same concept we're going to solve this. How we're going to solve this is going to be the same concept as this. It's on. Okay. So for here, it's only that the process is going to be much more longer. Okay, because here we can have this one, and then this one, and then this one, and then that one, and then this one. So we technically have 5 steps there. Okay, you can do it one by one, or you can write the whole thing as well. Okay, so the first one, we need to solve this side. Okay, we always start from where it is, which is -10. So that curve is Q equal to MC delta T, because it's a incline, so there's a change in temperature. So obviously you're going to use this. Okay, QMC theta. Okay, so then that is the first one. So this is, we can label it as ice. Okay, since that the mass is going to be the same, because the same ice is going to be water, the same water going to be steam. The same ice also going to become the steam. Only that this is going to be ice, sea ice. So the temperature also going to be the ice temperature. And then the next one is the next phase. So the next phase is here. So here the ice is going to be melting. So this is when the ice is going to the fusion melting process, where it is ml. Okay, ml L. So this is fusion. Okay, so then the next one is going to be this one. So M, the same mass, but this one C, water, and then the temperature change here is for water as well. Okay, so the last the fourth one is going to be here, is when the water start boiling. So it's a vaporization, boiling and then vaporize. So this is where we're going to put M equal to LV, vaporization. And then after that, after everything become steam, so the same mass as well, and the heat specific capacity will be the steam, and the temperature will be the temperature of steam. Okay, so the thing that you should note when you put the value, if you look at here, we can make things a little bit easier, because all these things have M, and then M is the same thing, so you can factorize the M right away. So you just put the M outside, so you're only left with the sea ice. So you write down the sea ice, 335 times 10 power of 3. Okay, that one. And then TIs. Okay, so this TI, you need to aware of this temperature difference there. So the final will be 0. So 0 minus 10. Don't forget this. It is minus of the value. Okay, and then after that you plus mass is with the factorize. So this one's only the latent heat of fusion. Where is it? Latent heat of fusion, which is LF ice there. Oh, I got it wrong just now. So this is not the heat specific capacity, not this one. This one is LF, is this one, C, 2100, yes. Okay, so that will be the value there. Let me just fix this one. 2100. Okay, okay, so the next one is M, also really factorized. So this is really going to be the latent heat of fusion. Latent of fusion is 335 10 power of 3. Then the next one is plus M. So this, I think M, the M we can just right away fill in the values. Okay, since that we already know the value, so 0.040. Okay, 40 gram. Okay, the next one is MC water. So M is already factorized. C water, water is going to be this 4,400. So going to be 4,200. And then the change of temperature. Okay, change of temperature here is also going to start from here and there. So it's going to be from 0 to 100. Okay, so here will be 100 minus 0. Okay, and then after that it will be ml. So m is already factorized. So this is right now is vaporization, which is this one. Okay, 2.26 times 10 power negative 6. 2.26 times 10 power 6. Okay, so that will be the value for LV. And then the last one will be steam. So mass already factorized. C steam is 1996. 1996. Okay, multiply by, so this is steam. Okay, yes, steam multiply by the temperature difference. So the temperature difference here is again from 100 to the final temperature described is 110. So here is 110 minus 100. So adding this whole thing will give you the final answer. Should get this answer will be the amount of heat required to change the 40 gram of ice cube into a steam of 110. Okay, so if you look at here, as we add up all this thing, the reason we add up all this thing, it is because of due to the direction of the increase of Q. But what if I were to do the same thing, eventually you're going to get the same, you can do it after this, you can do it the same thing. So this one you should get the answer 1.2 times 10 power 5. You try to put in all the numbers, try to do it again. Okay, let's see if you were to change the question just now. The amount of energy to be removed from 40 gram of steam at 110 degrees Celsius to form an ice cube, at -10. degrees Celsius. If you do this, you should get the same answer as this. It's only that you're going to get negative value. Okay, so how are you going to do in this case? In this problem, for this problem, you're going to add up the same thing like this. Okay, QMC del T, follow to the process, put in the value of accordingly. What the difference is that for it's going to start from the steam, so it's going to be the final going to be 100 minus 110. Okay, what about this? Okay, for the ml here, because it moving to this direction, this one you need to introduce the negative sign, so you're not going to be plus, you're going to be minus. So in general, the equation would be like this: mc steam, so I'm going to start with steam. So the temperature is going to be 100 to 100, from 110 to 100, which is 100 minus 110. You're going to get negative value for that. So here, because it's going to be condensation, it's not going to be plus, it's going to be minus ml v. We're going to start from here, from the right to the left, and then after that plus mc water. So the one that mc del T, you don't need to put the negative sign, as the final, the temperature difference will provide you the negative sign. Okay, so here the temperature will the final will be 0, because you want to reduce it to 0, and then the initial temperature will be 100, and then after that you're going to be minus, because for freezing, mlf fusion, and then plus the last one is mic ice. So ice is start from 0 to negative 10. Is it negative 10? Negative 15, is it? Negative 10, okay. Going to be negative 10, okay. Negative 10 minus 0, okay. So then you still get a negative value there. So add up this whole thing, you should get the same answer, the same value. It's only that it's going to be negative. Okay, try it out, see it. Okay, that's all. Thank you very much.